back to Engineer's Workshop. I'm finally ready to get back on the boring head extension, the Jig-Bore style extension to this Bridgeport number 2 boring head. We left last time with me getting flats on the sides and a circular feature both top and bottom, which I can indicate from. And that puts me in a good position to start putting in the holes on the sides. I got a couple of those to do, and the pocket on the bottom that will hold the carbide insert. So let me zoom you in here. I updated my drawing, and I'll show you what we'll be doing. This drawing's got a little bit busy, but main part on one side, we've got a drilled and tapped hole 3/8 24, which the purpose of that is to come in from the side. You can see it here. And it will push the actual extension of the boring head against that surface. That's the surface that when this cutter is turning is going to be in contact, and the cutting load is going to transfer back through to that surface. So that's the first one we'll put in. Then I'm going to flip the piece over on the bottom, bottom end facing up. And I have to put this pocket in, which I've blown up here. The bottom edge of the pocket is on the axis of the part. It's a 1/2 inch wide, and it's about, cleans up to about 3/4 of an inch deep. The dimension of these centers is 1.198 from the center of the part, and these are for a 1/4 inch diameter end mill. I originally had this at a 3/8, but the radius was getting in the way of that back corner of the insert. That insert is a 10-degree rhombus or parallelogram, so it goes back a little further, and is starting to rest up in that radius. So coming down to a 1/4 inch diameter end mill solved that. Actually, before I put that in, I'm going to put in the 2 mounting holes, counterbore holes for 3/8 16 socket head cap screws. And even though I have to put the K&T into drill press mode for this, you're going to see one of the absolutely outstanding features of this mill, which is putting in any size counterbore with a limited number of end mills. I'll drill the clearance holes, and then I'll probably use a 3/8 or a 1/2 inch end mill. I think these have to be, the counterbore diameter is 5/8, so I'll just go up to a 1/2 inch end mill and orbit a 5/8 diameter counterbore for the heads of those. Then I'll come back and I'll do this pocket last. Then that piece will be done. Mount it up, and hopefully get all that done in this video. And then the next video will be some test cuts. Probably do some test cuts in, I don't know, I've got some pieces of scrap here that I may be able to put in there and try that out, but I do want to get a little bit of time behind the wheel with it before I actually start using it in the radial arm saw casting. And I also got to do some roughing out on that radial arm saw casting to get that weld bead cleaned up and get it down close to the finished surface before I start using this. So over to the K&T, let's get started. Before we get back into the fabrication of that boring head, I wanted to show you something cool I picked up at an antique store. This is a Randall and Stickney snap gauge, and I believe this dates to the late 1800s. And it's basically so cool, I just couldn't pass it up. The anvil on the bottom has a vernier to re-zero it. And just look at this cool handle with the shape of a, baton over here on the end. It has a pretty long range. I think it's at least a 1/2 inch. And nice action, returns back to 0. And I bet you're thinking, what possible use could I have for something like this? Well, as soon as I saw it, I knew exactly what I was going to do with it. I'm going to sit it next to my pile o' drills, and I'm going to be able to determine what drill diameter I have. So that's a 214, because I cannot see the writing on these. There's the 1/4 inch I was looking for. Very, very neat tool. I actually got another one that is not in quite as good condition. Needs some repair. The gauge is stuck, but it's got a much deeper throat than this. The anvil's broken, so I'll get to make an anvil for it. But neat tools to have around. There's a few of them on eBay if you're interested. I drew some rough guides on here so that I can keep oriented as to what I would be doing. Got my 2 counterbore holes, the pocket, the side scallop and tapped hole to hold the ball in there, and then the tapped hole to come in and put pressure on the side of the extension. This one is 3/8 24 we're going to do first. None of the hole positions are super critical, so I don't think I'm going to spot them. I'm just going to pilot drill them and then through drill them for the tap. This one I'm going to over drill at 3/8, about half its depth, because the set screws, actually I don't know, just a little bit. I'll over drill it to 3/8 so that the threads don't run all the way out to the surface. To find the center line to set up for that first hole, I'm just going to use a little bit of math. I measured the diameter of the piece to be 4.022. I've got a 5/8 drill rod in the collet. I'm going to come up against a 10/1000 piece of shim stock, which I also measured, and that puts the center of the spindle. I have to move it 2.3335 or 2.334 over from here, and that'll be my center. In a similar fashion, after finding the top edge, I come in 0.3125 plus 10, 0.3225. Okay, the hole is a 1/2 inch in and 0.873. Let's slow this down a bit. I think that's about the last hole that drill's going to do without a regrind. I'm going to do maybe 1/4 inch at 3/8. That'll help me start the tap straight. I won't have to tap as far. Did 300 thousandths. We'll tackle the 2 mounting holes next, they're offset from the center 0.315 to the left and 0.873 to the right. So the through holes are easy, just locate, drill, pilot drill, finish drill. And the counterbores, like I said before, is where the K&T shines. I'll just take a 1/2 inch end mill, offset it, and this is a 5/8 diameter counterbore, so I'll need a 1/16 inch offset of the head, plunge down the 1/2 inch depth, and then walk a 360-degree circle, and presto, I have a counterbored hole for a socket head cap screw. Okay, I'm zeroed on this upper feature here, which allows me to set the position of those two holes. Same deal, except I am going to put a center in here. I don't like the way that 1/4 inch drill was wandering a bit as it started. Okay, our coordinates for these two are not on my drawing, so I'm going to have to go and reissue the drawing. I can hear my fabricators laughing their ass off because I've, occasionally have left a dimension off a drawing they got to call me for. So we got 0.873 off center for this one, 0.315 off center for this one. We'll spot them first, and then 1/4 inch, and then like 390. That's another drill ready for a regrind. That's a Chinese set. Surprisingly, held up surprisingly well for as long as they have. Drilled a bunch of holes with them. Some of them I have done hand regrinds on them. I think it liked the faster feed. Okay, so I've got my clearance holes here. I've got a 1/2 inch cutter in, and I need, for a 3/8 socket head cap screw, I need a 5/8 diameter counterbore that's a 1/2 inch deep. I'm not really concerned with sinking those heads in under this surface. Just as long as they're below that surface, I'm fine. So I'm going to just bring the cutter here until it touches the top. And I will drop the knee until I can get the cutter on 0. Excuse me, not the cutter, but my my quill feed. That's close enough. And the trick will be, cutters on, quill feeds on 0. I need to offset the head so that a 1/2 inch cutter will machine a 5/8 diameter. Difference between 1/2 inch and 5/8 is 1/16 of an inch, excuse me, 1/8 of an inch. So I need to offset half of that, the radius, of a 1/16 of an inch. So I'm at 0. I need to come out 10, 20, 30, 40, 50, 6. So that's 0.6, 2, 5. And to be proper, we're going to lock the slide so that it can't wander. Then all I have to do is start the spindle, plunge down the 1/2 inch, and rotate the head 360 degrees. And engage the head. We'll do this second one with compressed air, keeping the chips out of the way so you can see a little bit better what's going on. Last feature is the pocket that's going to hold the insert. I have it drawn on center. I think I might end up going a tiny bit below center, which is going to enable me to sink that insert a little bit deeper into the body, have less projection. I don't want a lot of unsupported edge here because we get our lead in from that upper edge, which is a 1/4 inch off that surface sticking out. That gives us a negative rake, and it gives us a clearance on the back side as well. So locating the two inner holes, or not holes, inner corners with a 1/4 inch diameter end mill is 1.199 from the center of the part. We'll zero up here, leave a 1/2 thousandths on that surface for future cleanup. These two centers are a 1/4 inch apart, so we'll basically mill out, come up, mill back, and then back to center, and then we'll just keep increasing the depth until we get a full 750, 760 depth that will let that insert sit fully in this, against this face. I set my incremental 0 at the innermost corner, and the way I did that was got a 1/4 inch cutter, so I came off 1/8 inch, which is the radius, plus another 5 thousandths. And that lets me have a cleanup cut. And then I'm basically going to mill outward. So I'm going to try 50 thousandths with this mill. Their corners don't look real great, but we'll see how it does. Trying to keep all the math straight in my head. So I went up an 1/8 inch plus 5 thousandths. My slot is a 1/2 inch wide, so I basically have to go up to a 1/4 inch on my incremental axis and then come back till my X reads 0, and that will be the extent of the slot. Able to do 100 thousandths increments at a time, which makes this go fairly quickly. Now that I've got the movements in the correct direction on the dials into my muscle memory, this is going pretty good. I need another full depth pass and then a 50 thousandths pass. Okay, I'm going to try to do a full depth cleanup pass along this back wall that the cutter will bear against, and that's 5 thousandths. That's how that cutter will sit. Tapping this 3/8 24. Love these spiral taps. I should know better than to tap underneath a sharp end mill. Final operation on the head itself is putting in this locating hole here for the set screw and ball bearing that holds the insert in place. I've played around with this thing, moving it in and out to get as much support as I can against that back face, plus have the right amount of stick out to give me some clearance from the cutter body. I settled on 1 5/8 inches from center line. I've had that as high as or as low as 1.611 and as high as 1.661, but I think that's a good compromise. That gives me about 45 thousandths projection of the insert itself. So there's like an unsupported leg of 45 thousandths at the tip, but that's a 1/4 inch thick insert. But that gives me a little bit more clearance to the body itself. So I'll show you how I set that up on the mill. I use my piece of drill rod here to get a 0 point at the top center of the face. And I need to come back a Y of 395. And I need an X dimension of 1.625. That locates the scallop in that surface. From the bottom of the mill at 0, I need to come down a depth of 758. Before I can put the head into service, I need to do a little bit of prep work on these set screws. Two different things. The one set screw that's going to bear against the side of the head, I don't want that cup point digging into it, so I'm going to turn this basically into a flat set screw. Then the other one is going to be modifying this cone so that it essentially goes from the outer diameter all the way in. That might take a fixture. So let's do the easy one first. Made a fixture out of a fine thread 3/8 coupling nut. I slit it, so I'm just going to load the set screw into it backwards. First thing I'll try is a brand new split point 3/8 drill bit. That's basically what I wanted, which was take the cone right out almost to the threads. Flat set screw on the side. I have both of my cross dowels positioned. I'm just going to get these till they're touching. And then I'm going to use this set screw on the side here to get good bearing on the thrust side of the cutting face there. And then I'll finish tightening down these. Might go a little bit even further in the head of the, when I mount it in the quill. Now this is going to take a little finagling. So we got that cone, which loads into this hole. But before That thing is seated. First, want to make sure that face is completely clean. I need to take a bearing ball and drop it into the pocket. And basically what will happen is that ball will apply thrust to this insert and jam it down into the corner. To put the insert in, I have to load a ball bearing into that hole, and there should just be enough clearance to slide this insert past. Now, the action of tightening this set screw should jam that insert down into the corner and set the correct projection. So I don't know if you can tell from this angle, but the axis of the set screw is lower than the axis of the ball and the hole in the insert. So that means the cone hits on this side and it bears in that direction to jam this down against that surface and of course against the back. Well, there we have it. Mounted this in the lathe so that I could get these a little tighter. We've got a set screw pushing. This is going to be pushing the head up against the inside block here in the direction of thrust on that cutter. A little bit of projection past the body. So I set up a fixture to do some test cuts with a piece of Schedule 40 pipe. It's basically the same diameter as the radial arm saw quill mount. Going to start on that on the next video, but I hope you enjoyed this. I'm chomping at the bit to give this a try, and hopefully it will work out and give us a smooth bore on that radial arm saw piece. Thanks for tuning in to Engineer's Workshop. As always, until next time, stay safe.